Hello. So far in our study of NumPy arrays, we have seen how you can access and modify the data in the array using indexing. And we've also seen how you can perform computations with that data using operations and aggregation. But we haven't talked much about how you would create that NumPy array in the first place. Well, we've seen a couple methods. We've seen the np.array constructor, but that works only if you already have the data in the form of lists or lists of lists, and that's not very common at all. We've also seen that you can load the data from a text file using np.loadtxt, and we'll talk a little bit more about that later. But what will most often happen is that you will build up and populate your NumPy arrays in the program itself. And to do that, you need to create and initialize the array in the first place. So now we're going to see the methods that are available to do that. This table shows 6 methods that you can use to create your NumPy arrays. The first two, arange and linspace, create 1D arrays with values that are evenly spaced. And the other 4, empty, zeros, ones, and full, create NumPy arrays of any shape that are pre-populated with certain values. So let's take a look at each one in detail. np.arange is similar to Python's range function. You'll remember Python's range built-in function, which was used to generate a sequence of integers, and we use that often in for loops. Now, arange is more powerful because it's not restricted to integers. You can have the start value, stop value, and the step value be floats. So, for example, the start value might be 0.1, the step value might be 0.1, and then the stop value could be 0.9. And notice here that the stop value is not included. So if you have these three, the last value in the resulting array is going to be 0.8. Also, the default value for the step is 1. Okay, np.linspace is similar to arange in that it also produces an evenly spaced sequence of values, except that instead of specifying the step, that is the gap between the values, you specify the number of values that you want to generate, so the length of the resulting array. Again, start, stop can be floats, but of course the number of values has to be an integer, and it's also optional, so the default value is 50. The other important difference between linspace and arange is that in linspace, the stop value is included. Okay, let's have a quick look at this in code. Let's go ahead and make an arange, and we'll do it between 1 and 4, print it out. We see now that it has values 1 through 3 because the 4 is not included. We can also see that the D type of this array is integers. It has integers in it. But if we change the step size to 0.5, then now we get the values ranging from 1 to 3.5 because still the 4 is not included. And this array consists of floats. If we make it from 1 to 4.1, then the 4.1 won't be included, but a 4 will be included. Okay, now let's try making a linspace. And we'll make it from 0 to 10, and let's put 20 values in it. So these are evenly spaced values from 0 to 10, and there are 20 of them. Now, the D type of this is obviously going to be a float. What if we went from 0 to 10, but we put 11 values in it? Now the gap between the values is going to be 1. So these could have been integers, but they're not. They're floats. They're still floats. And so linspace will always create an array of floats, while an arange might create an array of integers. The 4 array creation methods that remain, so we have empty, zeros, ones, and full, These take the shape of the array that you want to create, and they also take its data type. So when you call them, they know the amount of memory that you're going to need, and they can allocate a contiguous block of memory for you. And the idea is that later in your code, you're going to go back and you're going to fill in the array with the appropriate values. Now, that method is very different from what we did with lists, where we started with an empty list, and then in our for loop, we called the append method to grow out the list. You can also do that with NumPy. NumPy arrays also have an append method, but that approach is very inefficient. It's much more efficient to allocate a contiguous block of memory and then fill in the values. So here we have a quick example that hopefully will convince you, or that demonstrates this fact. What we're going to try to do is create an array that's called A, that's going to have values from 0 to n minus 1. And here n, I've set it to 1 million. Okay, so on the left we have the growing method, where we start with an empty array, and then we're ranging from 0 to n minus 1, and we're calling append, and we're appending to the array each value. And on the right, we have the pre-allocation method, where we first create an empty array with 1 million empty slots in it, and then we range from 0 to n minus 1, and each slot we fill in then with the appropriate value. And you can see here a drastic difference in the execution time. Doing it with pre-allocation is an order of magnitude faster than doing it by growing an empty array. So it's, unless you absolutely have to use the grow method, you should always consider pre-allocating, even if the amount of memory that you have to allocate you have to overestimate, because there's some uncertainty and you have to allocate a large amount of memory. It's usually much better to pre-allocate than to grow. Let's have a look at these 4 array creation methods. You can see that they all take the shape argument as an input, and that's going to be either an integer if what you want is a 1D array with a certain number of elements, or it's going to be a tuple if you want a higher dimensional array. So let's say you wanted an array with 4 zeros in it. Then I would say np.zeros 4, and we get a one-dimensional array with 4 zeros. If what I want is a matrix with 2 rows and 3 columns and all zeros, then I would pass in a tuple that has the shape 2 by 3, and now I have what I wanted. Now, don't make the mistake of doing something like this, where you say zeros 2, 3, because that's incorrect. You have to pass in a tuple or a list. Okay, now let's look at what is the data type that it's returning. The array has a data type that is float. We could also change that data type by passing in the optional argument dtype. So if I wanted this to be integers, I would just say dtype equals integer, and now it's producing an array of zeros, but these are integer zeros. Now that's important because, as I said before, this function is allocating a certain amount of memory, and if it's integers, it's going to be less memory than if it's floats. So once you have cast it as integers, you're not going to be able to store floats in there. So for example, if I say A00, that's the integer 0. And if I wanted to set that to 1, I can do that, but I cannot set it to 1.1. So it casts this 1.1 into an integer, and it saves it as a 1. So you save memory, but you also have to be sure that what you want is integers. np.ones is very similar to np.zeros, except that the values, instead of being zeros, are going to be ones. So nothing new there. How about np.empty? np.empty, if I want to make an empty array, say with 5 values, here we have it. So this is quote unquote empty. It actually has values in them, but these are junk values. And so it's understood that you're going to go back and you're going to fill in all of the values with the appropriate ones. Now, I like to use np.empty whenever I can because it signals to other programmers that my intent is to sweep and cover all of the values in the array. And if I don't do that, then the errors that show up are much more obvious than if I had used zeros or ones. So use np.empty whenever you can because your intent is to overwrite every single number in the array. np.empty also sets the data type. So if I have data type here, the default is a float, but if I wanted it to be integers, I could set it to integers, and now we have an array of junk integers. Again, much easier to find a bug if you were starting with this value than if you're starting with 0 or 1. Finally, we have np.full, and in this case, you're going to pass in the shape, let's say again 3 by 3, and we're also going to pass in the value that's going to be copied into every single position in this matrix. Let's say it's 10. Okay, so now we have a 3 by 3 matrix of all 10s. Now, it's going to try to infer what are the data types here. So if I look at the data type for this matrix, it's integers because what I passed in is an integer. If I had passed in a float, then it would say it's floats, but I can also do the explicit setting of the data type. So I could set it back to integer, and now it's integers, and these the value has been cast to integers. And so if I had done something like this, 10.7, it would truncate and keep only the 10 part. So yes, these array creation methods are very useful because they pre-allocate memory, they make your code a lot faster, and we're going to see how they are used in simulations and in engineering computation a little bit more in a future video. All right, I'll see you later. Bye.